of reinforced concrete. We're going to play a short video at the end of the talk if you want to find out more details. So tonight's talk is by Jens Fusing from BG&E Engineers. He has over 28 years of experience in structural engineering. He specializes in tall buildings, precast systems, and prefabrication. He's going to talk tonight about Esbjerg Towers in Denmark, a case study. He's going to address the question of can you build tall and affordable? So I'm going to pass you over now to Jens to start the talk. Thank you.
Yeah, thanks for that. Thanks for having me. Yeah, I'll just jump right into it. This is about a client who had some visions, some aspirations of building affordable houses, student accommodation with, what can you say, with complex architecture, and at the same time it has to be affordable. I met him a few years ago, and this is sort of the storyline from the, what can we say, from the aspirations to the end product. So his vision was to say, let's construct these towers or develop these towers up to 100 meters towers, which can be placed anywhere in North Europe. And he wanted to have the floor plates to be fully flexible, so you can have walls everywhere in the future. And then also the view outside from each apartment, he wanted to be a clear view from the floor up to the ceiling. And then this sort of architecture with the protruding facades. So this first project here, this rendering here, is located in Copenhagen. Sorry. Yeah. No, sorry. The other project is located in western Denmark, in Esbjerg. The two projects are located about 300 kilometers from each other and have very, very different environment, but the aspiration was to develop the towers at the same time so that you can sort of put them anywhere all over, what should we say, all over North Europe. This project here, Esbjerg Towers, ended up being also a hotel and a student apartment that was handed over September last year, 2021. Here you have some photos of the finished product. But anyway, this is the story about how to do it. And a lot of the, what can we say, the topics today is about prefabrication and how to, what can we say, do the prefabrication in a simple way, how to make something very, very simple, which looks very complex. Just to present the, what should we say, the stakeholders, the developer of this project here is called Materiais 2. The architect was Big, and the engineer of record was Big Engineering, and the third party consultant was a company called the Engineers. So here you can see on the map here. So over here, it's Copenhagen. That's where we have the Kaktus Towers, and over here we have Esbjerg Towers. So it's about 300 kilometers in between. It looks quite easy, but the environment is extremely different. There's different wind conditions, there are different ground conditions, and still up to 100 meters. So that was sort of the target of the development of the project. Here you have some of the initial architectural impressions about how it would be in Esbjerg to look over the North Sea. And if you can look far enough, you will see UK there on the other side of the ocean. I will jump a little bit between through projects as I move along, just for purpose of illustrations. So this is, for example, one of the before and after, and a rendering of the tower footprint, how the architect imagined it, and there over to the right here, you can see the end product of the tower columns and the central core, how it actually became to look in the end. So this is like a lobby. Yeah, so the floor plates, if you imagine that you have a central core and then you have all the walls, so all the rooms are almost the same at every floor plate, and each what can we say, each balcony rotates 22.5 degrees, whereas the internal layout of the villa is the same. So you can see that there's a lot of repetition here. Every single room is actually the same. The doors, the toilets, the facades, everything except for the balcony location on the outside. Here you can see the view of the soffit of the slab and from the floor. So that means that there are some constraints about drop beams and upstand beams. This was the architectural impression from the beginning, and this is a finished photo of the end product, and it is fully prefabricated slabs we're dealing with here, and again up to 100 meters. Yeah, if we just if we go a little bit back to some of the basics, because how do you ensure that the tower, how do you start correct so that you apply the first principles of tall buildings and prefabrication to ensure that the end product becomes as cost effective as possible? So for example, if you go to CTBUH, they have made these design handbooks, and they sort of have an order of what can we say, topics, which is cost drivers. So the worst cost driver you have is actually the shape of the tower. So the more clean you can make a tower up and down, the more cost effective it is. So again, from first glance, when you look at the Kaktus Towers, it looks complicated, and it doesn't really match to that shape thing. We'll come back to that one. So I call it a dilemma. The exteriors is sort of against what the rule of thumb is from experience. If you then go and look at how the material cost grows with height, then it's always usually it's always the slabs. For low-rise buildings, what is costing has the highest construction cost is the slabs, and then of course as you go up in height, then the stability starts to take over and your column grows. But the fundamental is actually the slabs. If you can make the slabs as thin and as light as possible, it will help on the stability, it will help on the column sizes. So we'll come back to how we dealt with the slabs. And just a few thumbnails about prefabrication. Usually when you do pre-stressed slabs like hollow core slabs or T-slabs or whatever, we should see a saving of 20 to 30% in the material self-weight, in the self-weight of the building. And we should also see a construction time which is about 30 to 40% faster than a conventional building. That's just thumb rules. And I'll show how we have applied that afterwards. And if you then look at some other thumb rules about what is called facade to floor plate ratio, if you have a very complex building, which we saw on the first slide, of course, the more complex the building looks, the more facade, the complex the geometry is, the more facade you will use. But if you just look at the math and say, this is actually from the pad here in the business bay. The pad it's leaning, yes, but the floor plates are rectangular. They're actually very long, about 1,000 square meters. So if you then measure all the perimeter of the floor plate, multiply with 3.5, then you have the area of facade and your facade to floor plate ratio. So if you then say you take the same area but make it square, then your facade to floor plate ratio will drop. That means you will use less facade along the perimeter. And the best geometrical, what can we say, figure is a circle. And if you notice, the buildings are actually round. We'll come back to that later on. So it's a thumb rule. So if you can apply these thumb rules to your tower, per default, you will start to make it cost effective from the beginning. The same goes for construction materials. If you go back to the 60s and before that, you can see that a lot of the towers around the world were predominantly steel towers, and then up through the generations, there's a more appetite for making them in concrete or mixed or composite. Why that is a long discussion. I'll not come into that. It's just a thumb rule. Concrete is good for tall buildings. And then if we look to the right and say, what do we also know? We know that the slabs are about 7.6 meters long in this project, from the core out to the perimeter. And at a certain point, it actually makes sense to pre-stress or post-tension your slabs. Usually I say around 6 meters, but this is a curve from a PT book. But somewhere around 6 to 7 meters, that's where it makes good sense to do pre-stressing. For example, if you have a hollow core slab is actually just air, right? So it always makes sense to do something which is pre-stress. So just to summarize on the high level thumb rules, what we have a tower with a lot of repetition. So we need to break that down into segments of the different trades and ensure that the repetition is continued. The building is round. The predominant construction material is concrete. The slabs are pre-stressed and lightweight. And we'll come back to and see how that was done. So in the initial stages, we did different models, and again up to 100 meters tall. Of course, the easy way would be to plunk in a few shear walls in both directions, or some outriggers, and then it will work. Because if you look at the aspect ratio, the diameter of the building is 24 meters, and if it's 100 meters, that's an aspect ratio of 4. So and we know from 5 to 8. That's usually where all towers will work if you engage the inner and outer geometry. But if you look at the core only, if you say the core was to stabilize the whole building, the core is only 7.6 meters in diameter. So if you say 100 meters and 7.4 meters in diameter, you get an aspect ratio of 14. So it was a given that something had to happen in excess of the core itself. After many, what shall we say, conceptual development, the outcome was to create a tube-in-tube system, because the tube-in-tube could also provide the, what shall we say, the flexible floor plates. And what we actually found out was that by the tube-in-tube system, torsion became the third mode, which is what we always want when we have tall buildings. So there were some benefits in all of those, what shall we say, investigations. So this was sort of the overall structural system and the initial analysis. When it comes to the slabs itself, we investigated everything from we have to read the story from the right to the left. So the first one was the traditional cast in situ with all the pros and cons. and we had a PT slab, and then we started to go into some precast slabs, some homemade rib slabs, and then we came into the SL slabs, which was, the thing was that the column spacing is about 4.6 meters, and 7.6 meters was the span. But this would actually have been the ideal shape if it was possible to transport it. One slab spanning from the core out to the two columns. I mean, the easy fix would be to have a radial beam which sits on the column and goes into the column, and then you have some small slabs spanning in between. But then you will have the issues with the MEP and the floor-to-floor height. So this was why all these different options were investigated. And if we look at the final one here, which is called option 1, here we had a slab which was split in the middle, and they were almost the same, all of them. So that one is the same as that one, same as that one, all the way around, times 3 towers. And these slabs here are pre-stressed and lightweight. I'll come back to how that was done. So that's what I said. I'm going to jump a little bit between some projects. The idea about having slabs in an unusual geometry actually came back from the tower boom in the zeros, where a lot of the towers on Esbjerg Road was done with fully prefab floors or semi-prefab. But what we did on many of the towers there was to say all the awkward geometry of the balconies, we would make them in that shape in a factory and pre-stress them. And why was that a good thing? It was a good thing because there were so many of them. These towers here are easily 40 to 50 floors. So that means for the factories, you had a constant repetition every single day. So thereby the cost of the slab itself comes down. So this is where the inspiration came from, those unusual pre-stressed slabs we use for the Esbjerg Towers. I just want to mention this here is the rib slab, which I say the homemade rib slab. This is actually used down on Nasta N1R. You have there are some footbridges between each building, and this is actually a section through the footbridge building. So you can see it's like a homemade hollow core slab. That the concrete, which is not really doing anything, you provide polystyrene instead of having concrete, and thereby it also becomes lighter. This is sort of the thought process behind it. This is just another project where we introduced these trapezoid shaped slabs in some water tanks. This is some water tanks which produces biogas, so it has to be completely sealed between the slab and the wall. So this was developed together with a company called A-Consult in Denmark, where we did these slabs here, and this is actually from UK. So they were shipped to UK, and that's where some of these ideas also came from. There's both from the Esbjerg boom back in the zeros, and here are some actual projects of a high repetitive amount of slabs for a water tank. So this is what I call version 1.0 of the concept development. Remember, we were working on the Esbjerg Towers and the Kaktus Tower at the same time. So this was sort of where one of the concept development ended. And here you can see we have the slabs, which is split in the middle, resting on some double high columns. I really like double high columns, even with you can see here we played with tube and tube. Say every other beam was moment stiff and every other beam was not, just to see where was the point of simply optimizing. Some with a corbel, which we knew the architect didn't want, some with a nip so we could hide the beam, but we still had the challenge with the upstand and downstand. I'll come back and show how it was actually solved. So this is like the raw version of the first crack at how could we solve the client's vision about the towers up to 100 meters. And this is then version 2.0. Here is how this is actually the drawing of the towers themselves. So here you can see that there's a beam at the edge resting on the columns. I'll come back and show some photos afterwards. And now the downstand beam has been removed. So what we did was we did a little upstand beam at the edge, which could then carry the self-weight of the two slabs out to each column. And you can see here how the slabs themselves, so the slab itself goes like that and has a recess and comes back in that way. And they were all having a splice connection at the middle. I'll show some photos in a while so you can see how it's done. This is the production drawing from the precast supplier called Esbjerg. So these are the SL slab. That's the name of the slab themselves. And here you can see how that little nip which sits on the column, and it has a recess around the column, and then it goes in and rests on the core wall itself. These bars sticking up here are the stirrups, which is going to be around the ring beam, which supports the ring beam. Does a lot of things, but of course it carries the self-weight of the two slabs out to the two columns. So the SL slabs themselves consist of some expanded clay, which can be found in the ground, which is like clay which is heated up. Then it becomes hard, and it actually creates both insulation and fire protection, and it becomes lightweight. So it's a little bit like a hollow core slab or double T slab, where you have something which is light. So the concrete itself is small T-beams, which is cast down between the clay. Here you can see how the molds were built, and the reason why these slabs became cost-effective was because of the high repetition. I mean, the factory could run for 4 or 5 months doing the same every single day, not changing any molds, and therefore you can also say that the waste was almost at a minimum, because there's normally when you have hollow core slabs, you have to cut something and you just throw it out, whereas here there is no waste at all. So for example, in this case here, this clay here gives the fire protection up to about 2 hours. It can also be done up to 4 hours. The beauty about these slabs is that they also work for diaphragm. I'll show that in a few slides. So here you can see some of the end results of the slab. Remember the architect's vision about not having anything stepping down, so he could look directly out, having a window. Here you can see the little recess about how the slabs are actually sitting on the column. And here that is the recess resting on the column itself. And this is the portion of the column which continues all the way up. And notice this tie reinforcement. We'll come back to that tie reinforcement. So in each column there is a tie reinforcement which is connected to the facade, which goes back into the core like a column tie. We'll come back to what that does. And of course, no downstand beams and no corbels, which was the architect's dream. Here we have some photos of the erection itself. Notice how few laborers there are on site. So 2 laborers and 1 crane. That's all for erection of these slabs. If you notice the castellation, you see the side of the slab there, and we know we have the bars also, the tie bars. So the diaphragm action itself is about finding out how does the load goes around and what happens, what's the twist. So the castellated joint is the way you can transmit shear forces from slab to slab. So that was also some of the benefits, and you can also you saw from the photo that you can provide top reinforcement in the slabs. One of the ideas we had, if we had to go up to 120 or 150 meters tall, was actually to use these slabs here as moment stiff beams by providing top reinforcement. Of course, that needs to be connected into the wall and all that stuff, but it is actually possible. Just a little fun detail: if you notice here, when the slab is lifted up, the railing is already fixed to the edge of the slab when it's lifted up, so you have a safe environment right after the slab is lifted up. The downside of the system here is that we have to splice the slabs at the middle, and therefore we have to have temporary propping of the slabs at the midspan of the two slabs. Here is some of the MEP integration before and after, how that was done. So if we just talk a little bit about the ring beam itself. So the ring beam does a lot of things. It carries the load from the slabs out to the columns. Then it also participates, and it removes the corbels. But we also have a thing: as soon as you are more than 15 stories, then you have this CC3 consequence class 3. We have also consequence class CC3 plus. We need to have a third-party reviewer on the project, and also there's a special set of robustness criteria which kicks in. You have the normal robustness criteria, but you also have the criteria about progressive collapse. And the way we sorted it out was because the ring beam was sort of in balance all the way around. Of course, one thing you can do is you can take a column out of your ETAP model and then see what's happened, and then you reinforce for that. But this one here was actually done a little bit more traditional from the old BS 8110, where you had the catenary action, where you can simply go in, the formulas are there, and then you calculate, if you say a column collapses, what is then the reinforcement required to carry up that load which is missing at the middle. And it was actually accepted. We managed to convince both the municipality and the third-party engineer, and also Big Engineering, who was the engineer record, and it became quite a cost-effective solution. We did also check by the ETAPS method, where you just take out the column. But I like it that you can actually bring it down to something super simple, and it's now a pre-accepted way to do the construction. So if you remember the bar I talked about over the column, which goes back to the core, so those bars are of course there for robustness, but they're also there to take the push-pull from the projecting or the protruding balconies, because you will have push-pull forces because of that overturning moment. If you look at the ring beam, so this is the ring beam at the middle. This is where we're between the two columns. So inside the ring beam itself, there are some cast-in steel plates, and on top of the cast-in steel plate, there's another steel plate, which is then being welded on site, and that is the one which is transmitting the way you can say the positive moment from the bars up into the plate and back over to the other bar. So that's done with a splice connection, and that's why we need to have that temporary propping. It's because of transportation, because you can't transport a 4.6 meter times 7.6 meter long slab in Denmark. We can here, but there you can't. So that's why it was split in the middle. And here you have a section of the upstand beam itself. Yeah. Here are some photos of the construction itself. It's sort of in the middle of the process, middle of the project. and the core itself. So the only thing which was not prefabricated was the central core that was cast in situ. And in my mind, it makes perfectly sense why the core was cast in situ, because just because you can prefabricate doesn't mean you have to prefabricate everything. If it makes more sense to do a cast in situ core, then you should do it, because you can make a circular, what should we say, a circular core precast or prefab. But the challenge is the lifts. They become very heavy. A core wall, which is 400 millimeter thick, plus the joints, is usually the shear between two joints, which is challenging with projecting bars, and then also the horizontal joints. How do you do that? If you do that in situ, it's very, very easy to do that. So and in this case here, as you can see, the core never became on the critical path, so it didn't matter. It was the sort of the right thing to do for this project here. Just some few topics about the core itself. Over here to the left, you can see all the stuff which sits inside the core. That was all prefabricated. The elevator shaft, the MEP shaft, the stairs, everything was prefabricated. Here you can see some more close-up. But one of the fun thing was that from the software which was Rivet, the contractor chose to make a little 3D model, to print a 3D model of the core itself, all the different items, the landings, the stairs, the inner core, the elevator shafts, so that the workers could practice before they came to site. They knew what, just like a little Lego set. So they were sitting there and playing with the components, so they knew what they were going to see before they actually went inside the tower itself. Of course, you can do this with all the virtual technology, but you can also do it like this. And I like this way of just it's a very good way to illustrate how the whole thing works. I'll just jump a little bit. If you remember that upstand beam, you can say here in UAE, nobody likes upstand beams because it's considered to be expensive, because you need to do formwork. There's a little bit change in the way that that buildings are constructed in terms of cooling and heating. So for example, this is from another tower we did a few years ago called Esbjerg Towers in Copenhagen. But the flooring, the way why we do this upstand beam, I'll explain it here. It's because of, if you have the, what should we say, the slab itself, then on top of the slab, usually you will have 150 to 200 millimeter of lightweight concrete, where you put in your floor heating, which is like hot water in some pipes, which is then integrated into that layer. And that's why an upstand beam makes sense, because then you can cast out to that as your reference point. This picture here is after that. So all of these, so the toilets in the Kaktus Towers is pods, prefabricated pods. So instead of making a recess down into the slab, they are just located directly on the slabs because of the floor heating. That's sort of the construction methodology is, and that's why. So it's very unusual to see recesses in the slabs there for the, what should we say, for the pods. On the master in 1R, we also had pods, but there we had to do recesses about 75 millimeter everywhere, simply because of the structural screed. We had to build down into the structural screed itself. Just some funny differences between what should we say, countries, and if you cool and if you heat, just some different some things to reflect on. If we just look at the wind environment of the two projects, so the one here in Copenhagen is away from the North Sea, so whereas the one in Esbjerg, which is to the west here, is very close to the North Sea. And actually, if you go to the Danish local annex of Eurocode, all the west coast here has a higher wind speed than the rest of the country. It's simply because of the predominant wind direction is northwest. And this is some screen dumps I took from a few hurricanes which hit you can say the North Sea, also UK, Norway, Denmark. Actually, this winter here, there was 2 hurricanes, and it's very normal that we get hurricanes 1 to 2 numbers per year. It's totally normal, which we don't get here. I just want to reflect a little bit about the wind environment here and there. So of course, because it's Eurocode, then it's the wind speed we use is a 10-minute mean wind speed. So we cannot compare that to our wind speed we use here for the 3-second gust. But I'm just showing here, even though it's in Danish, you can see here the colors. This is actually the 3-second gusts, which was measured at that night when the hurricane hit. And you can see a lot of these numbers here. As soon as it's purple, that's very close to what we're having here. I know we're saying 38, but that we can compare directly. And the reason why I'm bringing this up was that if we have gusts around 28 to 32, and I tell you that coast out here, it's always windy. I mean, the trees are leaning, not because of wind, but because they're trying to, it's just like sequential construction. They're trying to counterbeat the wind, but they can't. So all the trees, if you go there, all this line here, they will be leaning, all of them, at least 10 kilometers in from the coast. It's a very, very rough wind environment. And if you cut the tree in the middle, it will look like this. So the core itself in the tree is totally off center because the tree is trying to fight up against the wind. I'm just reflecting about, are we having the right wind load here? Because the wind environment for even these gusts here is very, very brutal. And if you then look at the inner side of you can say it's called Øresund here, the little sea between Denmark, Sweden, and Norway here, where all the water, of course, gets pushed in. There are some landscape which is very similar to, you can call Dubai Creek. And this hurricane here was over 24 hours from when it started until it clinked off again. Of course, it was very intense for the middle 12 hours. But if you see how much the sea actually rose for these gusts here, almost 2 meters. So my point is that if that happened here, what would happen to Dubai Creek? My point is, I still believe that the wind load we are having here is too high, because if all of this was to happen, the creek would be flooded. And this happens here, it happens almost 2 times every year. It's normal. And the reason why we don't have any purple colors up over Norway is because all of this here is mountain, so it's very, very rough landscape. So anyway, we did the wind tunnel study of the project, and one of the learning things, yeah, here you can see the difference in wind speed at the coast and at the rest of Denmark. So again, at first glance, when you see the project with the architecture, with the protruding balconies, you think this is not good. But it was actually. It did exactly the opposite. The way the facades, the balconies were, the geometry and the location did that, that the vortex shading was reduced. It actually reduced the wind load. If this would have been a nice, clean, round building, the wind loads would have been bigger than what we have here. Of course, with the same, with the same area. So that was one of the interesting findings from the project, that the geometry actually helped. And here are some illustrations of what the vortex shading looks like from way up in the sky. If we then look at the challenges with the foundations, the two again, the two plots are very far from each other in geographical sense, but only 300 kilometers physically. So if we look at Copenhagen first, underneath Copenhagen, actually all over North Europe, you will have this limestone layer. But in Copenhagen and other areas, it's very, very close to the surface. So you only have a little layer of clay, say for example in Copenhagen, which has been compacted by ice ages over and over again. Of course, there has been 5 main ice ages, but there's also been these interim ice ages. So the soil in Copenhagen is extremely good as soon as you get down into the glacial layers, because you have compacted clay and then you will have your limestone further down. So if you look over here, you can see this green line here. The last ice age we had didn't cover Denmark. So this is Esbjerg right here, and you can see it better here. So this is where the last ice age actually stopped. So all of this landscape, which is this pink landscape, was just like if you imagine you have the glacier front and then you will have melting water, which sort of makes the soil loose, a little bit like here. I know that it's not created the same way, but it's just like it's not compacted. Of course, you can find compacted clay and you can also find the limestone further down, but the upper 5-10 meters of soil is actually very loose, just like the Middle East. So you can say in Copenhagen we had the very, very hard soil, very well compacted soil, and then in the other, within 300 kilometers, we had the very, very soft soil, like sand. Yeah, so the way we did it was, again, we built the ETABS model, the SAFE model for both of the ground conditions. And of course, we started with the raft up to 100 meters, and of course a compression only member to make sure that you have compression everywhere. For the smaller towers, we didn't have a raft. It was normal, to say, pile cap foundations. But it actually worked. So in hindsight, it was quite easy to build the raft and put in the different soil conditions. And if you look at a result of the two analyses, the towers in Copenhagen, which is sitting on a very, very stiff soil, are driven by shear capacity. You can, of course, minimize your raft thickness, but it's shear which governs because it's a non-flexible soil, whereas the one in Esbjerg is a loose soil. So therefore, the moment was governing for the design itself. If we then look at the facades, if you see here, the facades are all the same geometry, because all the columns have the same geometry. In reality, there are only 4 different panels, but all the geometry are the same. The reason why there's different panels is because of the top, you want some views, and there's also some sun orientation, some U-value stuff which needs to be looked at. But the basic idea is that every single panel is the same. So if you notice these hooks here, we'll come back to those. There is a panel, and then there's a little middle piece panel also where there's some hooks sticking out. So in between this little middle panel, the normal curtain wall panel hangs on the traditional curtain wall system with a hook, where it slides down into the it sits on hooks. And these facade panels is produced by a company called Hansen Group. And again, if you remember the facade to floor plate ratio, this is even better, right? Because it's segmented. So the facades are not round, but the shape is round. So it's an optimum when it comes to prefabrication. If we look at the balconies, then you can see we have this middle panel with these hooks sticking out of the facades, between the facades. This is the workshop drawing from the balcony supplier, and how he broke down the whole system into components. So in reality, there are four different. It's 4 + 4 because there's also mirror. So those, but we can in general say that there are 4 different balconies in total. So when you see how again, the repetition factor. It's amazing how much it does good for a factory, and the erection time is amazing. I mean, but the same with the facades. I think it was also 2 days for 2 men and a crane to erect facades. The same with the balconies. We'll just come back to how the balconies were fixed, connected to the building itself. So we have this middle panel with some hooks sticking out. You can see these hooks here. These hooks here are sticking out. And that's it. They're back to the ring beam and the floor built up with the floor heating system, the SL slabs. So this is where we have the columns. So this is a section right before the column itself. So in front of each column, there are the hooks. You can see the hooks coming out here. They are then connected to the column. The column has a tie bar going in to the core wall. That was the one we showed before, which was both there due to robustness, but also due to diaphragm action and also due to the overturning of the overturning moment from the balcony. So it does 3 things, that tie bar. And here we can see the hooks themselves, how they are connected to the column, ready to receive some fin walls. So between the balconies, there is a wall from each apartment, so you can't see into each other's apartment. And this is the fin walls, which is then connected to the slab edges. So the fin wall is a structure itself, which of course takes wind load, but it also carries the self-weight of the balconies and brings the load back into the columns, and then you have the push-pull. Here you can see some of the construction at the construction stage of some of these fin walls, how it looks. And here is a photo of, this is from Esbjerg Tower, the other one was from Kaktus Tower, but here is how the balcony itself is connected to the fin wall. So the balcony itself does not touch the building. It only sits on the fin walls itself. And then they are repeated up through the building. These balconies is produced by a company called HB. I'll just show some photos or some images of the building, of the final product. Some night views, and I forgot to say that the railings are actually skewed because you have different fin walls on the 2 sides of your balcony. So the railing follows the shape of the building. Yeah, some more photos from the construction itself. And here, I really like this photo here because this was what the client had imagined and the architect. A completely flexible floor plate where you can do whatever. You can actually see the temporary supports there. This is where we have the splices, which has to stand there for some time until the concrete is cured. So this was the price of, you can say, of temporary supports because of the splitting of the slabs themselves. So yeah, is it affordable? Yes, it is. If you have a lot of repetition in your design, if you start out having a grid system which is all the same, respect all the fundamentals, ideas about prefabrication, and also our thumb rules from high-rise. Today, this building here is a student accommodation and also a hotel. I'll just show a few photos of the hotel, because this is where it comes in. Here you can see here, this is a double. So in the student accommodation, the room is from column to column, but because the floor plates are flexible, you can also play with room sizes. So this is some of the hotel at the upper levels in some of the towers. And I mean, you can see the exposed soffit of the slabs. You can see the view, the architectural intent, the aspiration about having that clear view from top to bottom. here are some images of the common areas in the bottom of the project, in the lower ground. Some more photos, and the exposed concrete, the exposed sprinkler systems. Some more renderings of the balconies and the facades themselves. A few more views out over the city. And I think, yeah, there's another one here. I think in some of my ending comments and reflections about this project here, because I have worked back and forth between Europe and the Middle East and actually used knowledge both ways around. I think to evolve as an engineer or as a company, you need to be stimulated sometimes, and you need to be inspired by other ways of thinking and other ways of constructing, and you need to be challenged and also provoked. And I do believe that if you work in an environment like that, then innovations will occur. And also what we see here is that there's in UAE there's a big push on innovation because of sustainability. And I mean, a lot of these ideas here would fit right into a more sustainable Dubai. I mean, minimizing of waste, minimizing of labor forces, minimizing of materials. So that's why sometimes it's good to come around and get inspired, not only by geography, but also different trades. For example, work as a bridge engineer, work different ways of looking at things, and then you can apply that knowledge to other fields afterwards. Yeah, I think that's it.
Jens, would you be able to allow me to start my video?
Yes, how did we, just a minute. I'll just stop sharing. Yeah.
Okay, thanks very much, Jens. It's a very, very interesting topic. We just have a few questions for you. First one is, was there a structural topping added to the concrete slabs to assist with any diaphragm action?
Yeah, this is also one of the what we say big differences between North Europe and Middle East. In Denmark and South Norway, Sweden, there is no earthquake. So that means that the horizontal loads are only there from wind or notional load. And if you look at it and say, at a certain point, the diaphragm action cannot be achieved because the loads are too big. So for example, I have done some project out here in Higher College of Technology. There, it was some low-rise buildings because it's a school. Out there, if you just compare wind to earthquake, it's about factor 5 to 8. We're doing some other schools right now, some refurbishment, which was constructed in the 80s here. There, it's a factor 16. So 16 higher load when you compare earthquake to wind. It will never be possible in just a normal hollow core slab with tie reinforcement. So therefore, you need the structural screed to take care of the earthquake. And then when you have the structural screed, you can also use it for composite action. If you roughen the top of the slab, then it sort of has a dual purpose, both for build up, maybe for some roof shape and some diaphragm action, and also the composite action of the slab. So that's the reason why we didn't have it there, simply because the loads are very small compared to here.
Okay, thank you. The next question is, you can see quite a lot of work went into the detailed design of the project. What software was used for the design and the detailing?
Well, for the structural analysis, it was ETABS for the structures itself, and for the detailing was done in Rivet as a BIM BIM technology. That's what was applied.
Okay, thank you. And there's one other question. It's not directly related to structural engineering, but there was two lift shafts. Looked to be two lift shafts in the building. At what stage did you end up having to increase the number of lifts in the building?
Yeah, that's a good question, because in our dream about having the 100-meter tall tower, the tallest one was actually only 86 meters. But it's correct, at a certain point, you will need wider staircases, you will need more MEP, you will need more elevators, especially if we were imagining a situation where we go to 120 or 150 meters. Then, of course, I don't believe that the dia 24 would work anymore, simply because the core would grow, and therefore the footprint of the building would grow. So yeah, that's the next what can we say, development to look into.
Okay, that's it for the questions, Jens. I'd really like to thank you very much on behalf of the regional group here in Dubai. I know it's not the first time that you've given us a talk, and hopefully it won't be the last time also. You can really tell what's striking from the photographs and the presentation is how few people are on site, which can only be a positive thing when it comes to health and safety. So thank you very much. What I'm going to do now is we're just going to play a short video from our sponsors, Spytech.
Hello respected engineers in the field of construction. I hope you're having a wonderful evening. We are the proud sponsor of the UAE regional group of iStructE in Dubai. We are luckily related in business as you are structural engineers, and we take care of your needs on the construction site. This is Michael Rafati, Marketing Manager of Spytech Corporation. Spytech is a Canadian company dedicated to producing software for structural engineers, and in particular, software for detailing concrete high-rises. One of our best-known packages is called Spider. Spider gets the analysis and design results files from ETABS, SAP 2000 or SAFE, and details that in AutoCAD. What it gives you, in fact, is the real shop drawings of all the elements of a structure at an unbelievable speed. For example, the detailing work of a high-rise normally takes some weeks or maybe a month or so. By Spider, however, it takes just one single day. One day. Unbelievable, right? If you want to see that for yourself, I invite you to a short video clip explaining the detailing functions of Spider, and after that I will be with you again. So as you saw, Spider details all the structural elements of your project while checking ACI and Eurocode. Therefore, coming to articles, codes and provisions, things like that, your mind is fully at ease with this software, which is the result of 25 years of development. I'm telling you something. Spider is revolutionary software in the construction, and this is the response we received from different countries, including the UAE, China, Australia, New Zealand, India, and countries in South America. Now, I have good news for you. We are going to have an online presentation describing the detailing functions of Spider soon. I encourage you to go to spytech.com and subscribe to our newsletter or follow us on LinkedIn in order to be notified about the date of this webinar. Thank you for watching this video clip. Final word. you will soon hear from Spider, the detailer of structures, everywhere in the world. So, for the time being and right now, please go to speedtech.com and check out the cool features of Spider. Thank you.